also think that what we did yesterday, just kind of a quick recap of it. So we proved that if you have a continuous map from U1 to U2, where U1 is some open subset in Rn, and U2 is some open subset in Rm, and F is continuous, then we basically saw that the graph of this map, okay, x is in, we say, U1 is a smooth manifold. It's a smooth manifold of dimensions n plus n. Okay? Now, if I take, for example, n equal to 2 and m as 1, then graph is going to give us what? So it's going to give us a surface actually. Okay. Then, okay, obviously, for defining surface, you need to have a patch actually. In other words, you need to have a map. Okay. In other words, you need to have a chart map actually. Okay. So that's a part of R2, and you have a map. Okay. And we kind of give this map a name that is going to be X actually. Chart map is exactly opposite of it, because a chart map is a map from manifold to R2, but you can treat this X as a inverse of chart map. Okay. Anyways, so we learned in what is called 3D calculus that some surfaces are, if this X map is good enough, okay, not getting into all those conditions, but the key thing was that if the XU cross XV of this map is always non-zero, then the X defines the surface actually. And what do I mean by X? X is a map that takes a point from 2D and gives me a point in 3D, and that point is basically UV and X of UV. Not X of UV, but some F of UV. F is some, what do you call, a continuous function. So we know from this that this is going to define, or its graph is going to define a manifold. Okay. And what would be this guy? So this guy would be what we call the local parameterization. Okay, local parameterization of the surface. It's not a global one because you may need parameterization, but we know that for chart, okay, what was the chart map for? What was the chart map for the graph manifold? It was basically identity maps, actually. Not identity map, but projections, kind of. So one way it was projection, and another way it was what was it? Was it identity? Projection and its inverse, actually. Okay. Yes, projection and its inverse, and its composition gives you identity on U1 and U2. Anyway, so recall all these details. So graph is a manifold, so this guy is a manifold, and will be our rest of the life. Basically, this course is going to be we're going to spend time on studying such kind of objects. Okay? That's what we think. What we did yesterday basically was one thing, that if you have a surface and you have a local parameterization of it, okay, then on this surface, if I draw an arc, okay, maybe a curve, how can I compute the length of it? In other words, if I have been given 2 points, and how can I roughly compute the natural distance between those 2 points? Okay, and how do we computed it? We computed it through something that classically you can watch the video for the details, but we know that if I want to compute this on a given surface, I need to what? Do what? I need to take the dot product of dx with dxn. Okay? This. And how can I compute this dx if x is this guy? Then the dx is going to be xu, that's a partial derivative, du plus xv and dv. It's dot product with itself. Xu du plus xv and dv. And after taking the dot product, it's going to be xu du square plus 2 times of xu dot xv du dv and plus xv dot square and you say dv square. No, not xv square. xv dot xv. Okay. And then we give these guys name. I call this quantity as E, which is xu dot xu, and F as xu dot xv, and G as xv dot xv. Okay? In other words, the df square can be, in other words, this small natural distance can be, infinitesimal distance can be computed by, if you know these two quantities actually, df edu square to f du dv and g and dv square. And this guy is called the first fundamental form. Okay. So the first fundamental form is basically it's a way to compute these natural distances onto the surface, small natural infinitesimal distances onto the surface. Now obviously every surface has a different parameterization. We know that sphere has a different parameterization, torus has a different parameterization, cylinder has a different parameterization, hallosoid has a different parameterization. So all these surfaces are defined through certain functions actually, and they have different parameterization. So these E's and F and G's will change. So in other words, this formula would change for every surface. So if you want to do geometry, you want to do things basically on a particular surface, you need this first quantity. Okay? What is this quantity in Euclidean space? We know that in Euclidean space, I can, so E is 1 and F is 0 and G is 1. Okay? In Euclidean space is just simply du square plus dv square. Okay? I can put all this into a bit more modern formulation. For that, I would say that let's take U1 to be U, and U2 to be V, and X1 to be XU, and X2 to be XV. Okay, and by parameterization, I'm going to mean that it's a map that takes this U1, U2 and gives you what? 3 components basically. So it will give you the coordinate maps x1, x2 and x3, where each one of these xi's are basically the function of these u alpha. Okay, so each one of these xi's is the function of u alpha. Okay, so with this notation, and I can also say, there's another interesting thing that I would like to add, that on this point, for example, I take a particular point, okay, and I consider a tangent space on this point, okay, then I know that there is a metric in R3, what you call the Euclidean metric, okay. This tangent space, which is basically the collection of all tangent vectors, okay, on this space. I'll talk more about it. to inherit the same metric actually. It's going to inherit the same metric. Okay, so naturally on this tangent space you have a metric. And by metric I mean, okay, not a metric but inner product. Let's be more precise. So on R3 I have inner product. I have a way to compute dot product, which is simply scalar product. And on the tangent space is a part of R3. Okay, and tangent space consists of vectors. Okay, so it's going to also inherit inner product from R3. Okay, and that inner product, which is what do you call inherited by R3, are the restricted inner product on tangent space. We call that the, you know, what do you call it? You can call it a canonical inner product. And then I know that I can define metric as inner product actually. So what is metric actually? So in order to see this, let me quickly draw another picture. So imagine I have a small patch in R2, and since this is in R2, I know how to compute distances here. So these are the lines actually, the principal directions actually through which I can compute the distance. And I'm now taking a continuous map and creating a surface out of it. So I'm taking it and bending it in some manner. So I'm going to get a surface, okay, as an outcome, and I'm going to get what you call these principal lines as well. Okay. But now these lines will be distorted actually. In other words, each of these rectangles will also be distorted. Okay. And now if I take a point here, okay, anywhere, then I can compute a tangent vector in the direction of, say, one of the principal direction. Okay. What would be each of these curves? Okay, so each of these curves is, for example, u1 equal to C. Okay, and this is, say, u2 equal to C. Okay. So each of these curves are representing basically the images of these lines actually under F. Okay, so on this point I can draw a tangent vector in the direction of, in u1 direction, I can call it xu or xu1, whatever. And I can draw a tangent vector in other direction, I can call it xv. And I know that using these two tangent direction, I can span a whole tangent space actually at that point. Okay? So so when I'm saying that I have a tangent space and that is spanned by these vectors xu and xv, then I can essentially write what do you call, and since this tangent space is inheriting an inner product from, you know, the ambient space actually, you know, the space in which the surface is setting out, then I can define what do you call metric tensor for this particular manifold. And what would be that metric tensor? So if I am taking what do you call G alpha beta, then G alpha beta is simply inner product of x alpha and x beta. And by x alpha I mean xu, so alpha could be 1 and alpha could be what? Alpha 1, 2 and beta could be u1 and u2. So these are what you call all possible product of these basic tangent vectors which are spanning this tangent space actually. Then I can rewrite this fundamental form in even more elementary manner, and that is going to be that I have a G alpha beta and D U alpha, you know, tensor product du beta. Okay, so this would be what do you call? So in other words, for every specific surface or the local parameterization of surface, or for every surface, these guys are going to change. And that is going to influence to change this first fundamental form. Okay? And first fundamental form is what is nothing, it's just a way to compute the small distances or the natural distances of manifold. Okay. So that was basically almost everything in the last discussion that we did. Okay? So today what we want to do, I want to discuss in detail intuitively and then a little bit more mathematically, depending on the time, that how to compute the curvature of the surface. So we are interested in the curvature, and that is essentially, the reason for this subject. That what we want to do, we want to compute the curvature of the surfaces, the manifolds. Okay, so if I say that why we want to study differential geometry, because we want to understand curvature. And curvature of what? Of manifolds. That's it. One line answer of a reason to study what you call differential geometry. And this explains a lot. Now, how can I study curvature? So the first description that I'm going to give is going to be completely intuitive. Okay, so just want to talk through, with pictures actually. Okay, and using those pictures, I would like to basically explain some of things, and then I will try to make them rigorous. Okay. There are many ways in which curvature can be represented for the surface. There are literally many ways actually. So I want to do in both actually. So like this guy adopts here, a bit more modern way to, introduce curvature, which is good. But the classical way is also beautiful. And that's also important basically. It's worth giving a look at, okay, how to measure curvature of a surface that is sitting in an ambient space. And essentially, what you are doing here, in general manifold, is just a state generalization. You just replace with everything, surfaces by manifold, so you're going to get almost the same thing. Okay. Obviously, things are going to be a bit more complicated there, but the essential idea would be same. Okay. So, how to compute how to understand the surface? How can I know? So, what is the curvature of this surface? So there is no curvature here. The question is, how can I say that this guy has no curvature? How about this guy? Okay, maybe this surface. Okay, this does have a curvature. So how do I say actually intuitively that this has curvature but this doesn't? So what should I do? Tangents, okay, I can find tangent in all lots of directions actually. Okay. It's not going to tell anything. The tangent plane is nothing, it's just a local approximation of what do you call the surface. Okay, so I want to take a point and I want to see if I see this tangent space, a small chunk of tangent space, a small chunk of surface is going to look like the tangent space. Okay, but naturally, the best way, okay, an intuitive way, are the what you call the Gauss genius was that he basically said that you can know everything through running a normal vector on a surface. So take a point. So on each point, I can find two tangent vectors. Okay, in the principal directions. By principal direction, I mean, these lines actually, okay, in principal directions, and consider the tangent space, spanned by that. And if you take these tangents, vectors in the principal direction and take their cross product, it's going to give you a normal vector. Okay? And what essentially you have to do is just move this normal vector on entire surface. And see, in other words, see the change or the move this normal vector in on the entire surface, and see the change in the tip of the normal vector. In other words, is it changing the direction? Okay, Because the change in direction of the normal vector is going to give you the information what the heck is going on the surface. So you just move on the surface, makes no difference. Okay, so it's like this tip stays same as it is actually. Okay. While if I, for example, move here, okay, so if I move in this direction, okay, so the direction of what do you call normal vector is changing in one particular way. But if I move, for example, so if I treat this as a sphere, so I can treat this as that. Okay, I had a part of 2D. I have kind of wrapped it basically using a continuous transformation. Okay, so it has two principal directions, a two-dimensional what do you call surface. So it's like a one principal direction is this, and the other principal direction is this. So what you have to essentially do is that run the normal vector in the principal direction and in all possible directions actually. Okay, and see what happens. So if you see that normal vector is behaving in one way, if you are moving, if you are roughly pushing it or moving it in a one direction, one principal direction, and if you move it in other principal direction, okay, for example like this, it appears that it's not changing actually. Okay, it's not changing. Okay, so this is almost looks like a slender. So if on slender I'm going up and down, I'm taking the normal vector up and down, is not going to change the direction. But if I take what do you call the curved path, okay, is gonna change the direction. But I can also go in this manner. So I can go from here. So I can fix a curve and I can move on it. So if I'm going not in the principal direction, but I'm moving in this manner on a particular curve which is other than what do you call these principal curves, okay, you're gonna say that you're gonna find what do you call the changes in the direction of the normal, and that is going to tell you, okay, that you are somehow curved. So imagine yourself blindfold in a car, okay, think about it, patti bandi hui hai, and a car is, you're sitting in a car, okay, and then you feel that basically that car is, so first of all you kind of pushed up, and then you pushed it down, and then you pushed up, and then you pushed down. So treat yourself or feel yourself as a normal vector actually. Okay, so you can, without even looking at the surface, in other words, the road on which the car is moving, you can still guess that it's probably the valley because I'm moving in a certain direction. And if you are if you are pushed to the left and the right, okay, sometimes you go this way and that way actually, so you can basically recognize that probably you are turning and twisting actually. Okay, so that's what is the trouble with us. This earth, okay, as compared to us, and hence this entire universe is like that we are nothing. We can't watch actually everything. So what we are watching is a very small chunk of it actually. So how can I know the curvature? When I see everything flat actually. Okay. So the only way to know that whether the space on which I am curving, okay, the space I am living is basically one of the possible ways to study these normal vectors. Okay, but one of the trouble with this normal vector of this approach is that you need an extra dimension, because surface is two-dimensional. You need a third dimension, and therefore you are saying that you can study the surfaces which are two-dimensional into the ambient space actually, which is three-dimensional. So you want three dimensions. So what eventually we want to do, we even want to throw away this ambient, space, and we want three. So that would be the ultimate theory of curvature actually. that in which you don't need to assume any underlying space. So you have a purely your manifold and you want to do something with it, okay, and try to know the curvature of it, okay. Doing this normal approach is kind of an extrinsic way to know that, this space is curved in a particular manner, okay. So we want to do both extrinsic and intrinsic way. Is it making sense? Okay, so pretty simple. Another beautiful thing that basically curved it, and it's just simply amazing. So imagine I have this surface, okay, and on this I have a point, okay, and this point can lie on many curves. Okay. It could lie on principal curves, which I'm going to give soon some name actually. Okay, but it could also lie on a curve which is something other than what is called principal curve actually. Okay, shall I get into this curve very for now? Let's not get into that. Let's get into it afterwards. Let's do things in a bit different. So let's imagine I have this surface. So Gaussian wave was this. He said, okay, if you take a point and draw tangent vectors and get a normal vector, okay, call this normal vector. This normal vector is going to be a unit vector actually. Okay, so we can turn this normal vector into a unit vector. Okay, and so it's going to have a magnitude 1. So if something has magnitude 1, what does it mean? Where does it would be? So it's going to be something on sphere actually. Something on sphere. Okay. So in other words, what Gauss did is that I want to compare moving on this surface with the movement of the same normal vector on a sphere actually. So let's consider this sphere. Okay. So I have a point and a point. I can have a map actually that takes me from this point to this point. P, some f of p. And on this I have this, what do you call, mapped normal vector, which is not necessarily in the same direction, it could be in any direction, depending on what kind of surface it is. Essentially what we can also do is basically this. Okay, you can do elementary thing. I can start from, take a point, I have a point here. Take a tangent vector, okay, and I can map this tangent vector to a tangent vector here. And take this tangent vector and map it onto this tangent vector here. And these tangent vectors are going to span a tangent space. So I can have a tangent space at a point. Okay? Basically what can I prove is that this tangent space, which is on my manifold, is basically isomorphic to the tangent space that I sent through some suitable map onto the sphere, okay, on S2. Okay? So that's what I can also prove. So that's what Gauss did actually. Then he said, okay, if this is the case, then what you can do is that, okay, you can take a point and draw a normal and move it and compare it with the movement of the way this, so you can also, you can say that somehow they are connected with each other. X simulation also we can run it actually very easily. So when I am moving this normal vector here, depending on the direction of it and the changes here, this normal is going to move here. Okay? And by seeing that how this normal vector is moving on sphere, I can have an estimate for the curvature of this, what you call the surface. That's what is the, what do you call, roughly the key genius of the Gauss was actually. Okay? And so let's take an example. Imagine I am on plane. and I take a point and I draw a normal vector. So analogically, I've got a sphere. Okay, and I have a point there. Okay, and I have a normal vector. Okay. So when I'll move this normal vector anywhere on this plane, would there be any change in direction actually?